Hi, Andrew Wolf here. In this video, I want to talk about the concentration of urine. Now, remember, we were talking about the glomerulus and Bowman's capsule. And so we have Bowman's capsule here with the filtrate forming. And, we have the proximal tubule. And then we have the loop of Henle. Now all the action sort of happens in the loop of Henle, so I'm going to sort of increase the size of it so we can talk about what's going on the inside of it. So this is, even though it doesn't look thin here, this is the thin descending loop of Henle. And then it remains thin until it gets about to here, and then it sort of thickens out. So then we have the thick ascending loop. Now, actually I don't want to write this too big here. So this is the thick ascending loop, but I'm going to erase that because we need to draw the collecting duct here. Alright, so it narrows down again, and I'm just going to make it back. I exaggerated this size of the loop of Henle so that I can draw things in it. And then we have the distal convoluted tubules, and it leads into a collecting duct, right? And the collecting duct drains other nephrons as well on its way down. Etc. Okay, so concentration of urine really occurs due to actions in the loop of Henle that cause concentration of the interstitial fluid and the fluid within the vasa recta. Again, the vasa recta is the vessels that wrap around. So the interstitial fluid at the top of the cortex is around 300 microosms per liter. And this is normal osmolarity for the entire body. So this is equal to normal plasma osmolarity. Now, the osmolarity at the beginning of filtration is about the same. Remember, because what makes filtrate? Well, it's made out of plasma minus the proteins, right? So the initial filtration equals plasma minus the proteins. So the osmolarity is going to be exactly the same. Now, various shifts occur during the process of reabsorption in the proximal tubules. Primarily, sodium is being reabsorbed, and then other molecules are following. But as sodium's being reabsorbed, water is following along with it. So by the time we get to the top of the loop of Henle here, we still have a osmolarity of 300 microosms per liter. Now, the descending loop of Henle can absorb, is permeable to water, but it's impermeable to solutes. So water can go in and out. Now, the opposite is true in the ascending loop of Henle. Water cannot go in and out, but solutes can. Okay? So keep that in your mind. Now, we're going to get to the meat of this as we start to talk about what's going on with ions here. So I'm going to draw a little cell. So we have a cell here, a cuboidal epithelial cell. And actually I'm going to draw a bigger picture of it here so we can really talk about what's going on in this cell. So we have this cuboidal epithelial cell at the thick limb of the loop of Henle. Now, at the basilar surface of this cell, that runs up against the vasa recta here, we have a sodium-potassium pump, sodium-potassium ATPase pump. So what does a sodium-potassium ATPase pump do? Well, it pumps 3 sodium out of the cell, and in exchange it pumps in 2 potassium into the cell. And because, remember, the potassium concentration inside the cell is pretty high, and the sodium concentration outside the cell is pretty high, so it's pumping against a gradient. So just so you remember, this requires the use of ATP. Hence, it's called the sodium potassium ATPase pump. And I know this is just a review, so we won't go into any more detail than that. So anyways, that's what's happening on the basilar surface of the cell. So we are pumping lots of sodium out and we're pumping potassium in. Now at the apical surface of the cell, we have what is called the sodium-potassium-chloride cotransporter. And this cotransporter works. This is called, this is an example of secondary active transport, right? Secondary active transport. Because this is using the concentration gradient of sodium in this cotransporter to pull in 2 chloride and 1 potassium. So this is called the sodium-potassium-chloride cotransporter. Sodium-potassium-chloride cotransporter. So we are actually pulling sodium-potassium and chloride out of the lumen of the urine. So what's important here, via these 2 steps, we are reducing the osmolarity of this urine, and at the same time we are increasing the osmolarity of the interstitial fluid and the fluid of the vasa recta, right? Because we're pulling, via these 2 pumps working together, we're pulling electrolytes from the lumen of the thick limb of the loop of Henle through the cell and into the interstitial fluid. Okay? So, if we're starting out with 300, an osmolarity of 300, nothing changes until we get up here, and then all of a sudden we have an osmolarity of 200, right? Why did this osmolarity drop? Well, because we pumped ions through the cell and into the interstitial fluid. So this interstitial fluid has now become higher concentrated, right? Now, these solutes cannot cross into here because the descending loop is impermeable to solutes, and water cannot cross out at the ascending loop because the ascending loop is impermeable to water. So because the descending loop is permeable to water, water gets pulled into this, down its concentration gradient into the more higher concentrated surface. Now these microosmoles stay the same in spite of that because of actions of the vasa recta, and I'm not going to get into that complexity here, but just what happens is when we pull water out of this descending loop of Henle, then what do? Well, we increase the osmolarity here. right? So now all of a sudden the osmolarity is up to 400. And since the filtrate is flowing in this direction, this is going to round the bend, and then we're starting here with 400. Now this obviously is going to get more concentrated again because we've got these pumps running here. So this interstitial fluid becomes even more concentrated. It goes up to 600. So what happens? Well, same thing. The osmolarity increases from 400 to 600, and this keeps flowing down the loop of Henle until we get here, and then the process continues to occur again and again until we end up with a very highly concentrated fluid. And maximum concentration is around 1200 to 1250. So the interstitial space in this entire area becomes very, very concentrated, right? We end up with a concentrated hyperosmolar concentration in this area. Right? And this extends to the interstitial space all around it. So we have 1200 microosms all over here. Now we are down here in the medulla, right? The medulla is where the juxtamedullary distal loops of Henle sort of hang down into. So just to localize where you are in the gross anatomy of the kidney, we're down in the medulla, and this would be in the cortex. Right? So this is, it is typical for our kidneys to have a hyperosmolar medulla. And it is all because of this, what's called the countercurrent mechanism of the loop of Henle, which is what I just described. Now, why does this help with concentration of urine? You know, it's interesting because this was very difficult for me to understand when I first read it, and it's taken me a number of years of teaching to really sort of wrap my head around it. What's sort of counterintuitive here is after the urine passes through the loop of Henle, it's actually hypoosmolar, right? It's dilute because of what's occurred here, because of this sodium-potassium-chloride cotransporter. It's become very dilute. So it remains dilute as it passes into the collecting duct. But where it gets interesting is when the filtrate gets down, drains down the collecting duct back into the medulla. The interstitial fluid is very, very hyperosmolar here, right? So if we have ADH present, if we have the hormone ADH, what does the ADH do? Well, it inserts little pores called aquaporins into the collecting ducts in the medulla of the kidneys. And so these are now open to water. Now we've got hypoosmolar urine here and a hyperosmolar interstitium out in the medulla, so water is going to quickly be pulled out from the collecting duct into the medulla of the kidneys. So this will allow us to, by water following its concentration gradient, it will allow us to concentrate urine nearly up to 1200, so up to maybe 1150. So that allows us to concentrate urine, and concentrated urine, what's the advantage? Well, it lets us conserve water. Conserve water, and volume. Particularly free water, right? Because we're talking about just water here. This is not electrolytes. Now, interestingly enough, there's a couple of different ways that we can block this, and we do. One way is by using a loop diuretic. What does a loop diuretic do? Well, a loop diuretic blocks the sodium-potassium-chloride cotransporter. So it interferes with the concentration mechanism so that we cannot concentrate our urine. Okay, so that's one thing that's very interesting. It blocks this process so that the concentration of the hyperosmolar medulla does not occur, or occurs to a lesser extent, so that urine is not concentrated, and that causes a diuresis, right? If you have unconcentrated urine, you are diuresing um, low concentrated urine, right? Now, the other thing that's interesting, and I think I talked about this when we talked about antidiuretic hormone, is that if you if you do something like drink a lot of alcohol, then you're actually blocking the formation or the excretion of antidiuretic hormone in the pituitary gland, and that will also cause a diuretic effect. So there are a couple diuretic effects that we are all sort of aware of in clinical practice and day-to-day life that occurs all because of this, of interference with the process of concentration of urine. Okay, I hope you enjoyed this lecture and it was useful to you. Please provide feedback by giving me a thumbs up in the button below. And if you have any questions, please leave them in the comments and I'd be glad to answer them if I'm able. I'm also going to put up a couple of links so that you can have quick and easy access to my other channels. And I hope to see you in future videos.